Good afternoon. We're moving on now to Chapter 2. Chapter 2 of the Essentials of Meteorology, a lesson. We're using the book, An Imitation of the Atmosphere, Essentials of Meteorology, and we're going to talk about warming and cooling Earth and its atmosphere. So let's go ahead and this is an interesting subject here. We'll go ahead and kick it off. All right, so the first thing we want to talk about is we want to talk about the difference between, we'll start with temperature and kind of explain that, and then we'll go into different heat transfer mechanisms, and we'll be able to go into that a little more in detail. So if we first take a look at the definition of temperature, so what exactly is temperature when we talk about it? Temperature tells us how hot or cold something is. It measures the average motion of the atoms and molecules. All right, so it's the average speed or average motion of atoms and molecules. That's what temperature is. Now, when we talk about temperature, we talk about average speed. We also have to mention kinetic energy. Kinetic energy, is simply put, is just a way in which we call energy of motion. When something's in motion, that particular substance or object possesses kinetic energy. Moving on to heat. Now, there is a difference between temperature and heat. Heat is the energy. Energy is the process of being transferred from one object to another because of the difference in temperature. So you may have two objects with two different temperatures, and heat is the process in which energy is transferred between those objects. And typically, heat is transferred from hotter temperatures toward lower temperatures, so warmer to colder temperatures. That's the way heat is transferred. All right. When we talk about heat transfer mechanisms, there's some very essential ones we need to talk about for meteorology. We will be talking about conduction, convection, and radiation. And we'll get more into that here in a little bit. Also, when we talk about temperature, we need to talk about temperature scales. And we usually measure temperature in 3 different scales. The first scale is the Fahrenheit scale, where freezing is at 32 degrees Fahrenheit and the boiling point of water is at 212 degrees Fahrenheit. For Celsius, the freezing point of water on the Celsius scale is 0 degrees Celsius, or that is a typo there, by the way. That actually should be Celsius, not Fahrenheit under Celsius. The boiling point is actually 100 degrees Celsius. All right. And then Kelvin. Kelvin is another way in which we can measure temperature. It's a more precise way we can do that, as 0 Kelvin is basically equal to negative 273 degrees Celsius. To get Kelvin, you simply just take the Celsius temperature plus 273. That's basically the way you get Kelvin. All right, so there's the temperature scales. We, of course, in the United States are most familiar with the Fahrenheit scale. When we're watching the TV weather report, for example, we generally hear the meteorologists talk about what the temperature is going to be in the 5-day outlook or 7-day forecast in Fahrenheit. So we're very familiar with Fahrenheit. Here are the comparisons of the Kelvin, degree Celsius, degree Fahrenheit scales, just showing you the differences. The 100 degrees Celsius, 212 degrees Fahrenheit, that is the boiling point of water at sea level. The hottest temperature ever recorded in North America was 57 degrees Celsius, or 134 degrees Fahrenheit, and that was recorded in Death Valley, California, back on July 10th, 1913, so that's the hottest temperature. 40 degrees Celsius, 104 degrees Fahrenheit, that's a very hot day. Usually you get that out towards the desert areas where it's much drier and the air has the ability to rise much more rapidly as compared to Pensacola, for example, or any other location east of the Mississippi River in the summer where it's way more muggy and humid. The freezing point of water, again comparing scales, 0 degrees Celsius or 32 degrees Fahrenheit, that's the freezing or melting point of water or ice at sea level. And then a bitterly cold day, for example, in the wintertime, that might be as low as negative 30 Celsius or negative 22 degrees Fahrenheit. And then finally, the coldest surface temperature ever recorded in the world belongs to Vostok, Antarctica, July 21st, 1983. where the temperature got down to a bone-chilling negative 89 degrees Celsius or negative 129 degrees Fahrenheit. Very, very frigid. All right, now we're going to move into a very important topic when we talk about heat. We talk about energy in the atmosphere, and that is called latent heat. Now, I would like to think of latent heat as the hidden heat. It's something that a thermometer cannot sense. It's a very important heat, though, in the atmosphere because it is the heat that is generally responsible for changing states of matter. Okay? When we talk about phase changes or change of states of matter, matter typically exists in the form of a solid, liquid, and a gas. And so we're most concerned in the atmosphere about phase changes between a solid, a gas, and a liquid. So latent heat, simply that is the heat energy required to change a substance or a state of matter from one form to another. And again, latent heat is a hidden heat. So it's not really sensed by a thermometer, for example. To be sensed by a thermometer, we would be talking about sensible heat, where we can actually feel it and we can measure it with that thermometer. That's sensible heat. Now looking at phase changes, okay, this is very, very, very important in the atmosphere because certain phase changes or changes of states of matter will either release heat or absorb heat from the surrounding area. Okay, so I would like to think of a couple expressions. Hopefully this will help you, a couple mnemonic devices. All right, free CDs are a hot release. That's the first mnemonic device I'm going to use. Free CDs, CDs as in compact discs, are a hot release. So free CDs are a hot release. Free is a shortened form for freezing. C, condensation. D, deposition. And what they do, freezing, condensation, and deposition, they release heat to the surrounding air. So heat energy is released to the surrounding environment. And that's shown here in the bottom part of the phase change diagram. Okay? Now, the other mnemonic device I'd like to share with you is cool, C-O-O-L, mesa, M-E-S-A. Cool mesa. Okay? So the M is melting, the E is evaporation, the S is sublimation, and the A in the mesa stands for absorbing heat from the surrounding air. Okay? So cool mesa. All right? Hopefully those will help. You can see here on the diagram again, we have melting, sublimation, evaporation. They will take heat energy from the surrounding air. And again, the condensation, deposition, and freezing, they will release heat to the surrounding air. Okay? And then you also notice, there's a very great amount of energy that's utilized during these phase changes. Latent heat is involved. If you go from a water vapor on the right to a solid on the left, or vice versa, from the solid on the left, the ice, over to a vapor on the right, this takes incredible amounts of energy from the surrounding air. So phase changes are very important. We're very familiar with melting of ice. If you were to take ice cube out and put it in a drink, and over time that there'll be heat transfer from the warmer beverage toward the colder ice. That colder ice would then be melted with extra heat energy added to it. All right, we're very familiar with some of these states of matter in our everyday lives. All right, just showing you again, these are some of the processes of latent heat. Another example of latent heat, I'm showing you here a thunderstorm cloud. When air tends to rise vertically and create these huge convection currents is what they're called. As the air rises and cools, we have what's known as a latent heat of condensation, and as we change states from a gas to a liquid through condensation, basically it releases a lot of heat, the latent heat of condensation to the surrounding air, and that can actually result in stronger updrafts in thunderstorms, for example. So this is just one application of latent heat. Here's another couple of, we're going to move right into the heat transfer mechanisms now actually. We're going to talk about conduction, convection first, all right? Conduction, I want you to think of conduction as simply transfer of heat from direct contact, okay? I'm going to show you a picture here in a minute to demonstrate conduction. But just remember that conduction is transfer of heat, and it says in this case from one molecule to another in a substance. But I want you just to think about transfer of heat by direct contact. And heat will always transfer from a warmer object to a colder object. Always, always, always. Convection is another form of heat transfer, and this typically happens on a warm summer day. Convection happens way more frequently in the summertime when the air is much lighter and much warmer and more buoyant. What I mean by buoyant is the air wants to rise because it's so much lighter and it's so much warmer and less dense. All right, so convection is, I want you to think of convection as transfer of heat in the vertical. So it's transfer of heat by the mass movement of a fluid, for example, water or air. In our case, we're talking about air. All right, so I'm going to go ahead and show you an example now of conduction. All right. So you see this person in the diagram holding, I want you to imagine that that's a pen, like a metal pen. It could be a utensil even if you want to imagine that's a utensil, a metal utensil. As you hold that pen or utensil over that open flame, what's going to happen is the molecules are going to vibrate very rapidly. The kinetic energy or energy of motion is going to increase. The molecules basically moving along that spoon or along that pin. That heat is going to transfer to your fingers over time, and that will cause you to drop that pin or that utensil, whether it be a spoon or a fork, if you hold it over open flame. You definitely don't want to try that at home because it can burn you in no time. All right. But this shows you an example. Conduction is by heating by direct contact. Holding that metal pin or that utensil is an example of conduction. Now, if I were to use this same diagram to basically illustrate convection, we think about vertical heat transfer for convection, okay, I want you to think of all that heat energy just coming up from the candle in the vertical, rising in the vertical. And as I'm making this video right now, convection is actually resulting in a thunderstorm outside my window, believe it or not. I don't know if you can hear the raindrops, but it's coming down quite hard right now. A lot of heat and humidity today across the area, and it's resulting in very strong winds and very heavy downpour outside my house right now while I'm recording this, believe it or not. All right, so there's a difference between conduction and convection. All right, here's just some different heat conductivities of various substances, okay? So, if there's still air or there's wood or dry soil, every substance is different in the way it conducts heat. All right, so still air has a much different value. Now these values, the heat conductivity is in watts per meter per degree Celsius. I want you to just pay attention to some of the higher values. Silver 427, granite, which is more of a rock, at 2.7, sandstone 2.6, ice is at 2.1 for heat conductivity. Then you have snow at 0.63, water at 0.60. What I want you to realize is heat conductivity, this describes a substance's ability to conduct heat as a consequence of molecular motion. Okay, so this is just showing you various, I just want you to get out of this image here that you can see different examples of substances and how they have different heat conductivities. All right, here's a really great example of what's known as convection or the vertical heat transport. All right. I would say the candle I just showed you in a previous slide, that's more of a conduction example. So if we use this as our primary convection example, I think that would suit us well. So the sun is out, as you can see in the upper left-hand portion of your screen here in this diagram. As that solar energy comes out of the sun, it heats the Earth's surface. Okay, and as that surface is heated, you notice the time periods there. You see how we started off with a hot surface at 2 p.m., hot surface 2:15 p.m., the hot surface at 2:30 p.m. What I'm showing you over time is a stronger thermal or a stronger convective air current. That's what a thermal is. It's just a strong convection current. And as you can see here, we're showing with convection the vertical transport of heat from the ground into the higher stretches or portions of the atmosphere in the vertical, from the ground up. And so as this convective cell gets stronger and stronger, or this thermal gets stronger and stronger, you'll notice that the thermal becomes more developed, it grows taller in the vertical, And this is an example of convection. The sun heating the surface, that less dense air wanting to be more buoyant, it rises in the vertical. Here is an example. Now, if I were to put conduction and convection back together here, you see how these air currents, these vertical air currents, these blue arrows, the hot surface, they rise above the hot surface. That again is your convection. All right. You'll see there's upper level winds aloft, and then you see there's also, besides the upward current of convection, there's also a downward current. So this whole convection cell or convective cell or thermal consists not only of an updraft, which is the up arrow, it also is composed of a downdraft. Okay? If I were to show you an example for conduction in this diagram, I want you to pay attention to that yellow hot surface. Conduction typically occurs in a much shallower area. It's not very tall in the vertical conduction. It's confined more closely to the ground. Alright, so now that we have described conduction and convection as two heat transfer mechanisms, we also have to talk about one final heat transfer mechanism, and that is radiation. Now, as energy from the sun travels through the air or space, it's going to basically travel in that medium, the air, in the form of electromagnetic waves or radiation. All things above absolute zero will emit radiation. That's theoretically the case. The higher the object's temperature, the shorter the wavelength of emitted radiation. So the hotter an object is, the shorter that wavelength of radiation is going to be. As the temperature of an object increases, the more total radiation is emitted. So what we're saying here is the hotter the object, the shorter the wavelength of radiation, and then we're also saying the hotter the object, the more total radiation that object can emit. Okay? Colder objects do not emit as much radiation as warm objects. Here is an example of the different types of radiation that are out there. If we were to examine the electromagnetic spectrum, you may have had the EM spectrum a while ago. Maybe you had it in, you go way back to high school, or maybe you go into more of your middle school, junior high levels. Maybe it was the first time you ever learned about this electromagnetic radiation. So there's different forms of radiation. There's the AM radio waves. Now, I just want to point out that the wavelength. What is the wavelength? The wavelength is simply the point from the crest of a wave, the highest point of a wave is a crest, to another crest of a wave. Okay? You notice with AM radio waves how much more distance there is in the wavelength between the two high points of the wave, or the crests. You'll also notice that the energy increases as I go downward on this chart. Next up would be television waves, the wavelength not nearly as significant or large. Then microwaves, we're getting shorter wavelengths. Infrared waves, even shorter. Visible light, look at visible light, how short the wavelengths are. See all those ups and downs in that line, how squiggly that line is? Ultraviolet waves, even smaller spacing in between waves. And then X-rays, even smaller. So when you go to the doctor and get those X-rays, you are on the very short wavelength, high energy spectrum area of the EM spectrum. Now, I'm showing next what's known as the visible light spectrum. Where does the visible light spectrum? Now, visible light is why we see colors. Why we see colors of the rainbow. Why we see, for example, a brightened sky or a darkened cloud. All right? It's all the way the electromagnetic radiation, way it hits our retinas in our eyes. But visible light is that portion of the electromagnetic spectrum in which we can actually see light and the differences of the light. Our retinas can detect the light within the visible light portion of the electromagnetic spectrum. This is the entire spectrum. On the left there, I'm showing you the radiation intensity, and on the bottom is the wavelength. Okay? So you notice, you may have remembered a mnemonic device in the past to describe the visible portion of the spectrum, and that would be Roy G. Biv. Red, orange, yellow, right? G was green, and then Biv was blue, indigo, and violet. It ranges from 0.4 to 0.7 microns on the EM spectrum. And visible light is that portion on the spectrum between ultraviolet to the left, see that? Ultraviolet, and then near infrared on the right. So that's basically where visible light sits. All right, and we're just showing you some differences now. Let's take a look at the difference between how the sun emits electromagnetic radiation, because it's a much hotter object, right? A much hotter object at 6,000 Kelvin. And on the lower right here of this diagram, I'm showing you the Earth and how it radiates energy. The Earth is much cooler. Look at the Earth's surface temperature. The Earth's temperature is at 288 Kelvin compared to the sun at 6,000 Kelvin. Okay? This is just showing you the wavelength. It's going to be much shorter for the sun as compared to the Earth because of how hot it is. Remember that the hotter the object is, the shorter the wavelength, the higher the frequency, the shorter the wavelength, and also the more energy is emitted. Okay, so there's a big difference here between the long wave radiation which the Earth emits on the right and then the short wave radiation that the sun emits on the left. Moving on now. Now that we have been introduced to radiation, okay, so in review, we talked about conduction, convection, and radiation as the three primary heat transfer mechanisms in the atmosphere. Now we're going to take into account the balancing act. So the Earth is trying to reach an equilibrium point all the time. There's no difference as far as temperatures go. So we're going to talk about a few terms here that help determine the way shortwave and long-wave radiation move through our atmosphere to keep the temperature constant or in balance. Alright, so radiative equilibrium, that's the first term we'll talk about. This is the rate of absorption of solar radiation. When I say something's equilibrium, the rate of absorption of something is equal to the rate of emission. So basically what radiative equilibrium is energy from the sun coming in equals energy going out by the Earth. Okay? So energy absorbed equals energy emitted. Energy being absorbed, pushed out by the sun to heat the Earth is balanced by the long wave radiation that's released as the Earth cools, for example, at night when the sun goes down. There's something known as selective absorbers, which are objects that selectively absorb and emit radiation. Okay? Some of our gases in the atmosphere are actually selective absorbers, and they may allow the shortwave solar radiation to come through, but they will not allow the long-wave Earth radiation to go back out to space. An example of this would be carbon dioxide, CO2. CO2 readily allows heat energy, the shortwave solar radiation from the sun, to readily pass through and reach the surface of the Earth, but carbon dioxide will not allow the long wave, the longer wavelength radiation from the Earth to go back out into space. Okay? Greenhouse effect. This is when the absorption of IR, infrared radiation from Earth, by water vapor and CO2. This is what causes a greenhouse effect. It's a warming effect. As the long wave radiation from the Earth tries to escape, after the sun goes down every afternoon, early evening, the Earth is trying to cool and release all the heat energy it received during the day from the sun in the form of longer wavelength radiation. Water vapor and carbon dioxide are two particular gases that are very selective. They will not allow that energy, that radiation from the Earth to go back out into space. So this diagram here is just showing you the differences. I know it's kind of small to make out, but there's a lot of basically different gases involved here, showing you the differences in the absorption and the wavelengths involved in different gases. I'm just going to kind of glean over this one really quick. I don't think that's as essential as when we talk about greenhouse effect, but it was just up there for your information. So greenhouse enhancement, we hear about this all the time on TV. We hear about, oh, the Earth is warming. We have greenhouse warming, global warming. All right. So we do have climate change. It is occurring due to increase in greenhouse gases. When we continually pump in carbon dioxide, methane is another greenhouse gas, nitrogen oxides, and chlorofluorocarbons, which we talked about briefly in Chapter 1, the CFCs, we abbreviate chlorofluorocarbons as CFCs for short, which tend to basically destroy the ozone layer. All these gases are, in fact, greenhouse gases. They act to cause the Earth to be warmer than if they didn't exist. If these gases did not exist, the Earth would be much cooler. So our Earth is much warmer due to these gases. Okay. there's something known as positive and negative feedback. So if I have a positive feedback, this is going to double the temperature rise. And just know that a negative feedback will decrease the warming. So something positive kind of amplifies something. Something negative tends to offset something else. All right, so again, what is overall the radiation equilibrium? Incoming energy, you can see by the yellow lines here from the sun, incoming solar energy is equal and opposite to the outgoing IR energy released from Earth. Now on the left here, I'm showing you without greenhouse gases, and on the right diagram, this is with greenhouse gases. Okay? So without greenhouse gases, all the long wave radiation from the Earth readily escapes back out into space. Okay? With greenhouse gases, however, look what happens when the long wave radiation represented by the red squiggly lines, when that radiation tries to leave from the surface of the Earth, some of it gets reabsorbed and re-emitted back to the ground due to the greenhouse gases, such as carbon dioxide, the methanes. The water vapor is actually the greenhouse gas as well, so it doesn't readily escape, and as a result, our temperatures are much warmer. Now, warming the air from below, the atmosphere does not readily absorb radiation. This is the selective absorber thing that I mentioned. All right? Due to the atmospheric gas composition, the atmosphere does not readily absorb radiation with wavelengths between 0.3 and 1 micron, the region where the sun emits most of its energy. On a clear day, solar energy will pass through the lower atmosphere with little effect upon the air. So I want you to think of the atmosphere with the gaseous compositions that we talked about with nitrogen, oxygen, the greenhouse gases. That readily allows the shortwave solar radiation from the sun to just reach down to the Earth's surface. That's all you need to take away from this particular slide. Here is the diagram itself, showing you the sun shining. You see the yellow lines there. Those are the short wavelength solar radiation coming in. And then you see the convection currents. You see how conduction is a very shallow layer near the ground. Okay, convection is that vertical rise of heat. And as the air rises and cools, we go from a gas, a water vapor, to a liquid through the process of condensation. And that condensation tends to release latent heat to the surrounding air, so that becomes more buoyant. Remember, the thermal or the convective cell consists of both an updraft, represented by the up arrow in the cloud, and then the downdraft outside the cloud where there's clear and it's blue sky. Okay? And notice on the right here, we have the absorption and emission of IR radiation by both water vapor H2O and the carbon dioxide CO2. Right, so as shortwave radiation streams from the sun towards Earth's surface, we have to talk about a couple things that may happen to it. So not all of the solar radiation reaches Earth's surface. Some of it is actually scattered. And the scattering results in the distribution of the solar light energy in all directions. The shortwave solar radiation can also be reflected, where more light is sent back to the source than scattered. And then we'll talk about something known as albedo. And all I want you to remember about albedo is it's the degree of reflectivity. Albedo is the degree of reflectivity. And different substances, again, tend to have different reflectivities. Okay? So when we look at shortwave radiation streaming from the sun, you notice how these different color lines, they represent, these are little air molecules, the little balls in the middle here. The sunlight's coming in from the left. You see that white arrow coming in towards the air molecules, which are scattered about our atmosphere. And you'll see how that light can be scattered, can be reflected, it can be even absorbed, which I really don't show here, but I want you to focus in on the scattering and the reflection, which we just went over. And that is represented by all these different colored squiggly lines away from these two air molecules at the center. Right, so shortwave radiation, the amount of shortwave radiation and what happens to it, whether it be reflected or scattered, that really is dependent on the time of day, believe it or not. If you notice in this diagram, we're showing you here at noon, the person standing at noon, that sun is directly almost 90 degrees right above the person at noon. So that's the highest point of the sky for the sun. Now when that sun gets lower in the sky, such as at sunrise and sunset, that light tends to be reflected much more rapidly off air molecules, because you think about this, look at the rays of the sun and how much more of an angle it is at sunrise and sunset before that light from the sun actually reaches the Earth's surface. So there's a lot more scattering or reflection towards sunrise and sunset. And we're lucky for that reason, because we get those really gorgeous red sunsets, those orange sunsets, because the fact that the sun is lower in the sky, lower on the horizon, and that results in a lot more scattering and reflection of the longer wavelength colors such as red and orange and the yellows that we typically see on the EM spectrum. Here is an example of albedo. Again, I just want you to think of albedo as reflectivity. Okay, fresh snow is has a very high albedo. It's very reflective. As shortwave solar radiation, the sun shines on a snowpack, 75 to 95% of that solar energy is reflected back off the snow. So therefore, there's no absorption of heat going on, and that is why a day with a snowpack is much colder than a day with bare ground, because of the high albedo of the fresh snow. Thicker clouds, these can also have a high albedo at 60 to 90%. Thinner clouds, it's respectable 30 to 50% albedo or reflectivity. Look at Venus. Venus has a 78% reflectivity or albedo. That's what makes Venus so bright in our sky at night. Then you have other different objects I showed here. The Earth and atmosphere has an albedo of 30. Sand has a 15 to 45% albedo. Water a 10% albedo. That's very low. And the moon only has 7% albedo. The moon does. So, the Earth's average temperature is 15 degrees Celsius or 59 degrees Fahrenheit. That's the Earth's, if I were to take a sample of the Earth's average temperature, just like our body temperature, our average body temperature is 98.6 degrees Fahrenheit. The Earth's average temperature is 59 degrees Fahrenheit or 15 degrees Celsius. And this exists because energy coming in from the sun equals energy being released by the Earth year-round. Okay? And so there is a big difference between seasons, for example, where you may have more solar energy there's more heat and solar energy reaching the surface than is leaving from the Earth. But in winter, that is flipped. So overall, throughout the year, there is a balance or a stable temperature, average temperature for the Earth. Okay? And then we receive different varying degrees of radiant energy. That's mentioned on here as well. Just want to show you that, how much Earth receives, how much it radiates, and what the surplus is. We usually have the energy surpluses in the summer season when the sun is much higher in the sky, the temperatures are much warmer, and we usually have an energy deficit in the wintertime with a lower sun angle. And again, it comes down to the fact, incoming solar radiation, for example, in this diagram, it comes down to the fact that the solar energy received equals the total amount of heat energy lost. So incoming solar radiation is 100 units in this diagram. 51 of those units are absorbed to the surface. They come straight down from the sun, reach the ground of the Earth. 19 units are absorbed by atmosphere and clouds. If you have clouds in the atmosphere, those tend to reflect a lot of light. 6 units are scattered by the atmosphere, by those molecules, those air molecules. 20 units are reflected by clouds, and then you have 4 units that are reflected from the Earth's surface. Just shows you the Earth's albedo. Okay. And this is an example of how energy gained equals energy lost, and that's how we maintain that 59 degree Fahrenheit Earth temperature throughout the year, over the course of a year. Energy in equals energy out. Okay, and there's a lot of processes involved in that. There's your shortwave solar radiation coming in, and again, just as there's a lot of processes involved, there's scattering, there's reflection of that shortwave solar radiation by clouds, by air molecules. You have different surfaces which heat differently. So there's a lot of different factors involved. But just remember that the radiative equilibrium or radiation equilibrium occurs because energy in or energy gained is equal to energy lost or energy out. Here is the Earth's annual energy balance. Now look at this. This is interesting. The most direct heating of the sun typically occurs at the lower latitudes at the equator, and you'll notice there's a surplus there of heat energy. Okay? And that's because the sun is generally fairly high in the sky year-round, between 0 degrees and 30 degrees latitude. And then there's usually a deficit, especially as you get towards 50 to 60 degrees latitudes. You typically have a deficit in which you have energy lost, more energy is lost than it's gained. Okay? So the overall Earth, the way the sun's radiation is distributed based on its solar altitude and its way it travels throughout the year at the different latitudes, that really comes into play with energy deficits and energy surpluses. But overall, it balances out in the end. Now we're going to move into a really fun topic. I really like this one. This one's the seasons. Why do we have seasons here on Earth? Earth generally revolves in an elliptical path around the sun every 365 and a quarter days. All right? So the Earth is not revolving around the sun in a circular path. We're in an elliptical path. As the Earth revolves around the sun, it also is spinning on its own axis. One spin or rotation is completed every 24 hours, and that is why we have 24 hours in a day. The way the Earth is tilted at its 23.5 degree angle, that results, as it revolves around the sun, that 23.5 degree tilt of the Earth results in a day being completed every 24 hours. Okay? We are typically closest to the sun at 147 million kilometers in January, and we're farthest from the sun here on Earth, 152 million kilometers in July. So now the question is, why is it not warmer in January? Well, we're closest to the sun, right? The reason being is in the wintertime in January, that solar altitude, or how high the sun is in the sky, is much lower. And as that sun is much lower, those light energy rays from the sun have to travel through a much longer portion of the atmosphere before they reach the ground. So by the time these faint, diffuse solar rays make it to the ground, they don't really contain as much energy. So it has to do more with the angle of the sun above the horizon, really, as to why, even though we're closest to the sun in January, that's something known as the perihelion. I just want to make that point. It's the perihelion. But we're still very cold in January, right? All right. We're farthest from the sun in July, 152 million kilometers, yet we're the hottest time of year in July. And again, that has to do with the fact that the sun is much higher in the sky, and that solar energy is much more direct. Okay, moving on. Distance is not the only factor impacting the seasons, as I just mentioned. The seasons are regulated by the amount of solar energy that's received at the Earth's surface. And again, this is exactly what I just covered. The solar energy received at the Earth's surface is determined primarily by the angle at which sunlight strikes the surface and by how long the sun shines at any particular point of latitude on the Earth's surface. So think sun angle here. All right, now this is a nice little picture we're showing. I'm showing you the difference between perihelion, which is the Earth's closest point of approach to the sun. And this occurs again in early January when the Earth is only 147 million kilometers from the sun. Aphelion, that occurs in July, typically early July, the 3rd, 4th of July. That's when the Earth is at its farthest most point away from the sun. I want you to pay attention too to the fact again that the Earth is revolving around the sun in an ecliptic shape. Not a circular shape, an ecliptic shape. Okay? You can see that here represented well. Now I like this because this really gives you a good idea of the differences in sun angle between the summer and the winter. The image there on the left, you could do this simply at home. Take a flashlight out, just put it down, shine it down straight, put that flashlight straight over a spot on a sheet of paper. Outline the circle of light created by the flashlight. Hold it directly overhead a point and draw the circle around that circle, okay? Where that light is. Then tilt that flashlight at about a 45-degree angle. and then draw a circle of where that light is again, and you'll notice the light, that area on the left, compared to the more direct where you hold the flashlight right above the paper. Look at the circle size difference. Much more spread out when you hold the flashlight at angle to a sheet of paper as compared to if you hold the flashlight directly overhead. All right, and on the right, that's represented here by the low sun and then the high sun. Again, in the summertime, that sun is much higher, so it's almost like it's 90 degrees of solar energy shining down, reaching the Earth's surface, as compared to the winter, where that solar energy is at a much larger angle. It has to cover a much greater surface area. Therefore, we have much cooler temperatures. This is a great diagram here, again, just showing you why we have seasons. So, you notice the white lines here through the Earth that are shown. This shows you the plane of the ecliptic, which is at 23.5 degrees. Okay? The Earth is always tilted at an angle of 23.5 degrees to the vertical. So 23.5 degrees. All right? It's revolving around the sun throughout 365 and 1/4 days, but it's also tilted on that axis at 23.5 degrees, the plane of the ecliptic. As a result, different portions are tilted towards the sun, different portions of Earth are tilted away from the sun throughout the year. Now, the autumnal equinox, September 22nd, and then the vernal equinox, March 20th. This is a point in time where there are 12 hours of day and 12 hours of night everywhere on the Earth's surface. Okay? At December 21st, we call that the winter solstice, or the first day of winter here in the northern hemisphere. The northern hemisphere is actually in the shaded area at the top of the globe. That is where it's tilted away. The northern hemisphere is tilted away from the sun on December 21st, the winter solstice. This results in less solar energy making it to the surface, and that results in our winter time here. Now, summer solstice, on the right-hand side of the diagram, that is when the northern hemisphere is tilted toward the sun. So you notice how the United States and the North Pole, that's more in the sunlight now on June 21st, the summer solstice. That means that we're getting a lot more solar energy. The sun is much higher in the sky. So the tilt of the Earth at 23.5 degrees on its axis, along with the revolution of the Earth around the sun, results in our seasons. Some major points, some good points, major dates to point out for you to remember. The summer solstice is June 21st. This is when the sun is most directly overhead in the sky. We have daylight, which is greater than 12 hours. Typically, June 21st in the northern hemisphere, that is our longest day of daylight, the longest amount of daylight we have in one day in the whole year. The autumnal fall equinox, which we'll be coming up on here, here towards the start of the semester, September 22nd, will be a little bit into the semester, but the sun is directly over the equator on the autumnal or fall equinox. Everywhere has 12 hours a day and 12 hours a night. And then the winter solstice around December 21st, just before Christmas, the holiday season. This is when the northern hemisphere is tilted as far away from the sun as it will be all year. And this is usually our shortest amount of daylight we get in a day on the winter solstice. So it's dark. It gets dark. It doesn't get light until later in the morning. You'll notice it gets dark a lot earlier in the afternoon. You're not getting much daylight. The vernal equinox around March 20th. This is the first day of spring. This is when the noonday sun shines directly above the equator. Again, at the vernal equinox, equal day, equal nights throughout the world, 12 hours a day, 12 hours a night, no matter where you're at in the world. At the North Pole, the sun rises above the horizon after a long 6-month absence. So that's the one really cool thing. At the northern latitudes of the North Pole, for example, they have 6 months of darkness from September 22nd, the autumn equinox, all the way to the spring equinox, completely dark in the North Pole. Okay? And then it switches after the vernal equinox. The sun finally comes above the horizon. That's March 20th. And it will stay above the horizon. Basically, it'll stay above the horizon all the way through to the autumnal equinox. So it's really cool. 6 months a day and 6 months a night generally occur at the polar areas of the Earth. All right. This is showing you this is a table, the length of time from sunrise to sunset for various latitudes on different dates in the northern hemisphere. This is showing you that at 0 degrees latitude, for example, there's generally 12 hours a day and 12 hours a night year-round. It doesn't matter if we're talking about the vernal equinox March 20th, the summer solstice June 21st, September 22nd, the autumnal equinox, or the first day of winter, the winter solstice December 21st. 0 degrees latitude at the equator, there's 12 hours a day and night year-round. As you go north, though, let's go down, let's say, to 50 degrees latitude. Notice March 20th and also September 22nd, as I mentioned, the equinox, both March 20th and September 22nd, the spring and autumn equinox, they have 12 hours a day and 12 hours a night everywhere. It doesn't matter what latitude. But notice at June 21st, the first day of summer at the northern hemisphere, at 50 degrees, there's 16.3 hours of daylight. On December 21st, the first day of winter, the winter solstice, that number goes down to 7.7 hours of daylight. Okay, and then you notice at 70 degrees, 80 degrees, and 90 degrees, as I was mentioning, the varying degrees of day and night for much longer periods of time, depending on the time of year. This is showing again just how on June 21st, how the northern hemisphere, the North Pole, is tilted or tipped towards the sun. So therefore you get more heating, or more light, more solar energy, more daylight in the northern hemisphere, showing you the different numbers of daylight at the different latitudes on the first day of summer, June 21st. All right, seasons in the southern hemisphere, just keep this in mind. They're the opposite of the northern hemisphere. So for example, our first day of winter, December 21st, would be the first day of summer in the southern hemisphere. So if you were to go take a vacation over the holiday break to Australia on December 21st, 22nd, 23rd, it would be generally around the first day of summer down there in the southern hemisphere. So just keep that in mind. Closer to the sun in summer, average summer temperatures in the southern hemisphere, average summer January temperatures in the southern hemisphere are cooler than the average July temperatures in the northern hemisphere. Just keep that in mind as well. The northern, we're going to talk about local seasonal variations now, and we'll talk about how in the northern hemisphere, objects facing south, they generally tend to receive more sunlight during a year than those facing north. Now, you wouldn't think this was very important, but keep this in mind. When we talk about construction of buildings, houses, where we live, vegetation, where we plant vegetation, how ski slopes are orientated. Do ski slopes, which want to keep snow nice in powder form, want to keep that snow on the slope for business, do they want to have a ski slope on a south-facing direction towards the sun or a north-facing direction? Okay. Landscaping, also, this is impactful. And then architecture in general. Again, northern hemisphere objects, in our northern hemisphere, objects facing south will tend to receive more sunlight during the year than those facing north. Here are the local seasonal variations again. Now I'm just showing you different latitudes here. North Pole is A, 90 degrees north. Do you notice at the North Pole how the sun generally tends to just not really show much fluctuation or change in its elevation? It's fairly constant elevation above the horizon or above the ground. If I go to Antarctic Circle now, we get more of a tilt, showing you the differences of where the sun is in the sky between the different seasons. In the mid latitudes where we live at 40 degrees north generally, you see how the June sun is much higher than the December sun. See how the December sun is much lower above the horizon? So this changes throughout the year, the height and the altitude of the sun throughout the year, and that really plays a big role in what kind of temperatures we get during each of the seasons. All right, that wraps things up today. This is Chapter 2 lesson. This is the summary. We're going to go over this real briefly. There is a difference between heat and temperature. Just keep that in mind. Heat involves the transfer of energy from a hotter to a colder object. That's what heat is. Whereas temperature is the average speed of molecules contained within an object or substance. Okay? We define the temperature of an object through its kinetic energy, which is energy of motion. And kinetic energy, generally the faster molecules and atoms move, the higher the kinetic energy and the warmer the temperature of the object. We cannot forget about latent heat. This is a hidden heat. We can't see it, we can't feel it, but it's very important, especially in phase changes. We talk about condensation, evaporation, deposition, sublimation. All those phase changes, those 6 phase changes, melting, all that, that has a big impact, latent heat, on those phase changes. Transfer of heat can take place by 3 mechanisms: conduction, convection, and radiation. Conduction was direct heat contact, convection is the vertical transport of heat, and radiation is in the form of electromagnetic wavelengths, especially emitted by the Earth and the Sun. And then the seasons, Earth seasons, we have seasons because the Earth is tilted on its axis as it revolves around the Sun. That will cause seasons, seasonal variations of temperatures. All right. Please feel free to send me emails as you need. If you have any further questions, I'm hoping these lessons are very helpful to your understanding of the atmosphere. Everybody, I wish everybody a great day, and I'll be in touch with everybody as we continue to move along.